Electricity is the invisible force powering our lives, lighting our homes, running our gadgets, and connecting us to the world. From your morning alarm to your favorite video game, nearly everything you do relies on a steady flow of electrical energy. But electricity doesn't just appear. It's generated at power plants using different methods, burning fossil fuels, harnessing water, wind, or sunlight, and most powerfully, through nuclear energy. Nuclear energy uses a special element called uranium, unlocking massive amounts of power without greenhouse gases. It's like discovering a secret code for clean energy. So, how do we turn a rock from the ground into the electricity that lights up our lives? In this journey, we'll explore the science and ingenuity behind nuclear power. Get ready to see how human innovation transforms the ordinary into the extraordinary. Let's dive into the world of nuclear energy. Uranium is the heavyweight of the element world, the heaviest naturally occurring element on Earth. It's a dense, silvery white metal found in small amounts in rock, soil, and even ocean water. To use it, we search for concentrated deposits called uranium ore, found in places like Kazakhstan, Canada, and Australia. What makes uranium truly special is its unstable atoms, especially uranium-235. These atoms are packed with energy and can split apart, releasing bursts of energy, a process called radioactivity. Scientists learn to harness this instability, turning tiny atomic bursts into a powerful, controllable energy source. Even bananas are a little radioactive, but uranium's radioactivity is the key to nuclear power. By splitting uranium-235 atoms on command, we unlock a clean, powerful source of electricity. This is the secret behind nuclear energy, using the unique properties of uranium to power our world. Let's see how we get this remarkable element out of the ground. Once we find uranium ore, after extensive geological surveys and careful analysis, it's time to mine it. And there are a few ways to do it, each tailored to the specific location and depth of the uranium deposit. The choice of mining method is crucial for efficiency and environmental impact. If the ore is near the surface, open-pit mining digs huge terraced bowls into the earth, creating a vast landscape of stepped layers. This method is effective for large, shallow deposits. For deeper deposits, underground mining creates tunnels and shafts like a hidden city below ground, requiring specialized equipment and skilled miners to navigate the complex network. A newer, eco-friendly method is in situ recovery, a technique that minimizes surface disruption. This involves pumping a solution underground to dissolve uranium and bring it up as a liquid, leaving the rock undisturbed. This process carefully manages the chemistry to selectively extract the uranium. No matter the method, the goal is to collect uranium ore and bring it to the surface, ready for the next stage of processing. But the ore is just the start. It contains only a small amount of uranium, mixed with other minerals and rock. At a milling plant, the ore is crushed and chemically treated to separate uranium, a process that requires careful control and monitoring. This process results in producing a bright yellow powder called yellowcake, a concentrated form of uranium. This yellowcake is the first step toward nuclear fuel, the raw material that will eventually power reactors. From here, the journey continues as we make uranium ready for the reactor, transforming it into a form suitable for generating energy. Mining uranium is a blend of geology, engineering, and chemistry, all to unlock the energy within, requiring a multidisciplinary approach. Next, we'll see how we make uranium super powerful, a process known as enrichment, which is crucial for nuclear energy production. Let's keep going. The story of uranium is far from over. Though yellowcake isn't ready for the reactor yet, it needs more of the rare uranium-235 isotope. Natural uranium is mostly uranium-238, but we need to boost the tiny amount of uranium-235. This process, called enrichment, is like picking out your favorite candy from a giant mix. First, yellowcake is turned into a gas called uranium hexafluoride. Then it's spun in gas centrifuges. Imagine a super fast salad spinner. The heavier U-238 moves outward, while lighter U-235 stays closer to the center. By repeating this process thousands of times, we increase the U-235 concentration to about 3–5%, just right for reactors. The enriched gas is now ready to become nuclear fuel. This transformation, from rock to enriched uranium, is a marvel of modern science. Next, we'll see how this gas becomes the fuel that powers cities. The journey from ore to energy is just getting started. Let's turn gas into power. The enriched uranium gas is converted into a fine black powder called uranium dioxide. This powder is pressed into tiny, super dense pellets, each one the size of a gummy bear, but packed with the energy of a ton of coal. The pellets are baked at high temperatures to make them hard and durable. Next, they're loaded into long metal tubes called fuel rods, made from strong, neutron-friendly alloys. Hundreds of these rods are bundled together into fuel assemblies. These assemblies are the final form of nuclear fuel ready for the reactor. From rock to high-tech bundles, each step is engineered for safety and efficiency. Now let's see how these fuel assemblies unleash their power. Deep inside the heart of a nuclear power plant lies the reactor core, where meticulously crafted fuel assemblies are carefully placed within a massive, robust steel vessel. This vessel is designed to withstand immense pressures and temperatures. Here, within this specialized environment, the magic of nuclear fission begins to unfold, a process that releases tremendous amounts of energy. It all starts when a neutron, a subatomic particle, strikes a uranium-235 atom, the primary fuel source in many nuclear reactors. This collision causes the uranium-235 atom to split, a process known as fission, releasing a significant amount of heat and, crucially, more neutrons. These newly released neutrons then go on to strike other uranium-235 atoms in the vicinity, initiating a self-sustaining and controlled chain reaction. Much like a line of dominoes falling one after another, each triggering the next. To manage this powerful reaction, control rods, made of materials that readily absorb neutrons, are strategically inserted or withdrawn from the reactor core to slow down or speed up the rate of fission. This precise control is essential for maintaining a safe and steady energy output, ensuring the reactor operates within its design parameters. The intense heat generated from nuclear fission is then used to boil water, transforming it into high-pressure steam. This powerful steam is then channeled to spin a massive turbine, which in turn drives a generator, converting the mechanical energy of the spinning turbine into electrical energy that can be used to power homes and businesses. After passing through the turbine, the steam is cooled and condensed back into water, ready to be used again in a continuous cycle. Nuclear power plants harness this intricate process to generate substantial amounts of electricity, providing a reliable power source around the clock. It's a remarkably powerful and efficient system, offering a source of clean energy derived from the very heart of the atom. While the underlying science is undeniably complex, the fundamental result is quite simple. It provides a dependable and consistent power supply for millions of people. Now let's delve deeper and explore some truly amazing and perhaps surprising facts about nuclear energy. The story of nuclear energy gets even more incredible as we uncover its potential and its impact on our world. Did you know a single uranium fuel pellet can produce as much energy as a ton of coal? Nuclear plants can power entire cities around the clock, using surprisingly little land. After years in a reactor, spent fuel still contains most of its original uranium. Future reactors could recycle this for even more clean energy. The uranium we use was forged in exploding stars billions of years ago. Every reactor releases ancient stardust energy. Nuclear plants are built with layers of steel and concrete for safety, and their buffer zones often become wildlife havens. Nuclear energy is a bridge between cosmic history and modern technology. It's clean, powerful, and full of surprises. Now let's see how nuclear stacks up against other energy sources. When we consider the future of our energy needs, a crucial question arises. How does nuclear energy compare to other methods of generating electricity? Let's delve into a comparison of different energy sources, examining their strengths and weaknesses in the context of a sustainable future. Fossil fuels, including coal and natural gas, have long been the backbone of our energy infrastructure, providing a reliable source of power for homes and industries alike. However, the reliance on fossil fuels comes at a significant environmental cost, as their combustion releases substantial amounts of greenhouse gases and various forms of pollution into the atmosphere. This pollution contributes to climate change and poses risks to public health. Solar and wind energy offer a cleaner alternative, harnessing the power of nature to generate electricity without direct emissions. However, the availability of solar and wind energy is inherently intermittent, as their output depends on weather conditions like sunlight and wind speed. This variability poses challenges for grid stability and requires energy storage solutions or backup power sources. Nuclear power stands out as a low-carbon energy source, producing zero carbon emissions during electricity generation. Furthermore, nuclear power plants operate continuously, 24 hours a day, 7 days a week, providing a steady and reliable supply of baseload power to the grid. This makes nuclear energy the most reliable large-scale clean energy source currently available, ensuring a stable electricity supply for homes, businesses, and critical infrastructure. Nuclear power plants boast impressive operational efficiency, typically operating at maximum power for over 90% of the time, demonstrating their ability to consistently deliver electricity. Nuclear energy can effectively complement renewable energy sources, creating a more resilient and sustainable energy system. Nuclear power can step in to fill the gaps in electricity supply when renewable energy production is limited due to unfavorable weather conditions, ensuring a continuous flow of power to meet demand. But what about the issue of nuclear waste? The volume of nuclear waste generated is relatively small, and it exists in a solid form, allowing for safe and secure storage in specialized facilities. This contrasts sharply with the millions of tons of carbon dioxide and other pollutants released into the atmosphere by fossil fuel power plants. In fact, all the used nuclear fuel produced in the United States over the past 60 years could be stored within the area of a single football field. When we consider the broader implications of energy production, taking into account factors such as reliability, environmental impact, and waste management, nuclear power emerges as a compelling option, offering unmatched reliability and contributing to cleaner air. It plays a crucial role in our efforts to combat climate change and transition to a more sustainable energy future. The future of energy lies in a collaborative approach, a partnership that leverages the strengths of various energy sources. This involves integrating nuclear power with renewable energy sources like solar and wind, creating a diversified and resilient energy mix. Let's now explore how nuclear energy directly impacts our daily lives, powering our homes, businesses, and communities. Nuclear energy powers our homes, schools, and hospitals quietly, reliably, and cleanly. It's a major tool in fighting climate change, providing carbon-free electricity on a massive scale. Beyond power, nuclear technology helps in medicine, diagnosing and treating diseases, sterilizing equipment, and even improving crops. The science of the atom has benefits far beyond just keeping the lights on. The future is bright. New reactors will be safer, more efficient, and produce less waste. Small modular reactors and advanced designs are on the horizon, making nuclear more flexible and accessible. Nuclear energy is a vital part of a clean, balanced energy future. It works alongside renewables to power our world and protect our planet. The journey from rock to electricity is a story of innovation, science, and hope for a cleaner tomorrow.